Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends, to your younger brothers and sisters who would want to take up engineering soon, and to your relatives. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So let's have the principle on the analysis of dams. So a dam is a hydraulic structure used to impound water for various purposes such as water supply, irrigation, recreation, fishing, etc. Power supply, power generation, for example. So here is a dam, and our interest here is the analysis and investigation of its uh, stability against possible failure of this dam. So we have this dam in general, which is submerged. So we have overflowing water. So if you were the dam, then this is the heel, this is the toe. So it's like the headwater is at the back of the dam, and the tailwater is the toe. So if the dam fails by overturning, so it's like the man or a person that is overturning also about the toe. So if it slides, then it's like it also slides forward. So the headwater is on this side, and we will denote the depth as h sub 1, and this is the tailwater. The depth is h sub 2. Then we consider, so that's the headwater, this is the tailwater. We consider 1 meter strip on its analysis. So we have here the vertical projection of this face, which is rectangular, and since we consider 1 meter width perpendicular to the cross section, because the dam has uniform cross section along its length, so that's why we have to consider 1 meter width. And the centroid of this projection is here, so the force FH1 would be below as shown. And the distance of the centroid to the water surface in the headwater is denoted by Hg, or barred H. Then this is FH1, the distance of FH1 from G. Just like in plane surfaces, it is denoted by E. And on the other face, we have FH2 on the tailwater. Of course, if this is the tailwater and it intersects on the body of the dam, then this is 2/3 of H2. So there's no need to solve for E. So the net horizontal force that pushes the dam therefore is denoted by FH net, and it is the difference between FH1 and FH2. So for horizontal forces, FH net equals FRX, and it is equal to FH1 minus FH2. Rx, by the way, is the, because we have here a resultant force which is definitely down to the right, then it will be transmitted to the foundation. Then the same resultant force which acts opposite in direction and equal in magnitude to the resultant of the forces acting on the dam. The x component or horizontal component of that force is denoted by Rx, and the vertical component is Ry. Next, we consider vertical forces. So we have here, we draw lines from the end of this point on the hill up to this level, because we have varying curve on the face, varying surface. Then we have another volume to be considered, this volume here and this volume here. Same is true with the volume of masonry as shown, and this one. So we will call this weight 1, and from the previous principle, weight 1 is simply the volume of this uh, triangular wedge of water. Volume 2 is the weight 2 is the volume of this rectangular wedge of water, and of course these weights pass through the centroid of that volume to be considered. And remember, we consider 1 meter width into the screen. Then this is W3. You can locate the centroids or center of gravity of these weights or these volumes from the toe. And it is not uh, indicated here, but later on when we compute for the righting moment caused by these weights here, you need to know the location of the centroids or center of gravity. So this is weight 4, then weight 5 for this masonry here, weight sub 6, weight sub 7, or in general up to weight sub n. So the vertical force or forces would be Ry, and the net Ry or FV net is equal to Ry, and it is the sum of the weights, vertical forces, minus uplift if there is any, if it is in considered, especially if the base of the dam is pervious that water is allowed to flow through underneath. So this is FV net, and the distance, this FH and FH net and FV net will have a resultant force which is down to the right if this is the configuration, and it will intersect the base, and the point of intersection with the base, the distance from the toe, is denoted by barred x or simply x. So this is the equilibrant, the resultant R, and we remove this and denote this with its components, namely Rx and Ry. So Rx is this FH net here, equal and opposite to that FH net. Ry is also the net vertical force, which is opposite to this uh, component of the resultant, and that is denoted by barred x. So this will be the expected soil pressure diagram due to these forces, including the effect of the uplift force. So this is the projection, horizontal projection of the base. The length of the base is denoted by B, and perpendicular to the screen or board, we have the 1 meter strip here. So rotation, if there is overturning to happen, would be about this axis here. So that this is important in the setting up of the moment of inertia of this cross section with respect to the axis of rotation, which is here. Then this is the base of the dam sectioned, and if there is uplift, it is normally higher at the heel. It decreases from the heel to the toe with a certain coefficient or percentage denoted in geotechnical engineering with K. So K1 gamma of water H1, then this is K2 gamma of water H sub 2. So these Ks here are specified in the problem in hydraulics. So this is the uplift force, which is equal to the volume of this uplift pressure diagram. Likewise, Ry is also the volume of this soil pressure diagram, which is important in computing the intensities QH and QT later instead of memorizing formulas for combined stresses in the mechanics of materials. So next, we have to ensure safety of the dam, we have to compute or evaluate these safety factors. These safety factors include factor of safety against sliding, which is Fs sub s, and this is equal to the ratio of the resistance to sliding, which is due to friction, divided by the net horizontal force, which is Rx or FH net. So in this case, this is mu times normal, and the normal is Ry. So coefficient of friction, static friction between the base of the dam and the soil foundation, mu sub s, times normal, which is Ry, divided by the net horizontal force, which is Rx. So factor of safety against sliding is mu sub s Ry over Rx. So that's the formula for factor of safety against sliding, and that should be evaluated to be greater than and equal to 1 so that the dam is safe against sliding. But for experienced designers, even if it is less than 1, about 0.9, because in the actual construction, in the analysis here, the dam is just standing over this foundation here, but in the actual situation, we have keys here, or piles, or portion of the base of the dam is embedded into the soil, so that it serves as the soil here will serve as a lock, but that is not considered in the analysis here. So that's why for experienced designers of dams, even if the factor of safety against sliding is less than 1, but zero point 0.9 something, that is still uh, allowed for brave and very experienced designers. But for the sake of theory, the dam is safe against sliding if this ratio is greater equal to 1.0. Then factor of safety against overturning, denoted by dot capital S dot sub O. This is equal to the resistance to overturning. Of course, overturning would be in this situation clockwise moment, because it is overturning about the toe, or tipping, and the moment which resists that overturning is called righting moment, and it is due to the moments due to the weights and moments due to this FH2 here. That's righting moment that will resist overturning, while overturning moment is caused by this FH here, FH net, and uplift, if uplift is considered. So this is equal to righting moment, which is in this case counterclockwise, supposedly due to W, depending on the orientation of the dam and the location of the headwater, minus overturning moment. Overturning moment in this case will be the clockwise moment. So factor of safety against overturning is righting moment over overturning moment. So righting moment would be the moments due to the weights, FH2. So since they are moments, then distance of the weights from the toe must be known, so that we can evaluate these righting moments. We can do that because these volumes are, or these areas are common areas. Then soil pressure should also be evaluated. The maximum soil pressure should not exceed the allowable bearing capacity of the foundation, which is supposedly specified if it is to be considered, if it is to be evaluated in comparison to the allowable bearing pressure. So it is equal to QH and QT here, and I will present two discussions on how to evaluate them. So Ry times barred X, Ry times barred X, summation moment about the two, Ry times barred X plus overturning moment clockwise equals or minus righting moment equals 0. So the value of barred X to locate the intersection of the resultant with the base from the toe, it is barred X, so it is righting moment minus overturning moment all over Ry. So that's the formula, but you're not supposedly forced to memorize that formula. If you're asked to find the location of the point of intersection of the resultant with the base, all you have to do is sum up moments about the toe, so that you will not memorize this formula. But if you can memorize that, the better, so that we can evaluate the soil pressure intensities right away. So Ry is volume of soil pressure diagram also. So another way of computing Ry instead of the combined stress formula is treat it as volume of this soil pressure diagram. So we have to divide the trapezoid into two parts. You may have it uh, solved directly as volume of this prism of soil pressure diagram, which is trapezoidal, and remember it is 1 meter into the screen, so it is area of trapezoid times 1, where the area of trapezoid is 1/2 quantity QH plus QT times B, distance between QH and QT, then times 1 perpendicular to the screen. So that's the value of Ry. We can also divide it Ry into two parts into this triangular uh, pressure diagram and another triangular pressure diagram into Ry1 and Ry2. So that the location of Ry1 from the toe is 2/3 of B. Location of Ry2 from the toe is 1/3 of B. So Ry bar x equals Ry1 times 2/3 of B plus Ry2 times B over 3, where Ry1 is 1/2 of QH times B times 1. So just volume of this triangular wedge. 1/2 of B QH times 1. Ry2 is 1/2 of B QT times 1. So that's it for another way of computing uh, the intensities QH and QT, because Ry1 can be computed in terms of QH, Ry2 can be computed in terms of QT. And remember, Ry is Ry1 plus Ry2. So you can solve for QH and QT in this case. So this is the good design if the location of Ry is within the extremities of the middle thirds, which will be presented on the next slide. So we have to evaluate if the dam is designed in a good manner if Ry falls within the extremities of the middle thirds. So as long as Ry falls within the extremities of the middle thirds, then it is a good design, whether Ry is closer to the heel or closer to the toe. But for me, we should allow the dam to slightly slide and to slightly overturn, or motion is impending for the two cases, so that the design would also be economical if we do that. So if we divide the base B into three equal parts, then these 2 points here, the points of division, the inner points of division, are called extremities of the middle thirds. So if Ry falls within that, or including this boundary, then we have good design. So that's the position of Ry because it is closer to the toe. The toe, remember, is on the right part. So that we have good design if the soil pressure at the toe is greater than that at the heel. So it should be trapezoidal, the soil pressure diagram. This is the center line. The distance between the center line and the location of Ry is denoted by E. So that's the toe, that's the heel also. That's B over 2, and that is E. So this is the projection of the base, and this is the base of the dam. And if that is Ry, we have to apply principles in static. One principle in static, we have to add two forces in equilibrium. It will not affect the original resultant, the resultant of the original system. But in this case, we have Ry upward, which is the same originally. This time it acts as the center, so that these two Rys here will be replaced by a couple, which is counterclockwise couple as shown, and the intensity of that couple is equal to Ry times E, because this is equal to E, the moment arm. So that if we apply the combined stress formula, sigma equals plus minus force over area, then plus minus mc over I, if you can recall. So this is the expected soil pressure diagram, maximum at the toe, then minimum at the heel. So this is the combined stress formula from mechanics of materials, where P here is Ry, and area is projected area of the base, which is B times 1. M is this Rye. C is distance from centroid, or center line, to extreme fiber, which is in this case B over 2. Then moment of inertia is moment of inertia of this projected area with respect to the axis of rotation or overturning, which is this. So it is 1, the height is B in this case, 1 B cubed over 12. So moment of inertia of a rectangle, remember, with respect to the centroid. So this is P over area. P is Ry, area is B times 1. We have plus minus. In mechanics of materials, if the stress is tension, then it is positive. But this is fluid mechanics and hydraulics. The positive pressure here is that one that is pressure or compression. So plus minus Rye, the moment, this is C, B over 2, and this is the moment of inertia with respect to this axis of rotation, 1 B cube over 12. If you simplify this, Q is plus Ry over B, then plus minus 6 Ry E over B square. Factoring out Ry over B, remember in fluid mechanics, the positive pressure is compression. So Q therefore is Ry over B, quantity 1 plus minus 6E over B. So this is the formula. As long as Ry lies within the extremities of the middle thirds. If it lies outside the extremities of the middle thirds, you cannot use this formula, but instead use the other interpretation that Ry is equal to the volume of soil pressure diagram, because that's the other way. You may forget this. You may just solve Ry as volume of soil pressure diagram and apply Varignon's theorem. You sum up moments about the toe. Then those two information or two suggestions or two principles are enough in computing the intensity of pressure of soil pressure QH and QT. You can also use this as long as Ry lies within the extremities of the middle thirds. Where E is absolute value of B over 2 minus barred X, or it is barred X minus B over 2, so we anticipate that Ry is always closer to the toe, so that's why it is absolute value of B over 2 minus barred X. If Ry is closer to the hill, then E would be greater than B over 2, so this formula is always true, correct. So values of soil pressure, so as suggested, you can use this formula if Ry lies within the extremities of the middle thirds, or the other formula, which is volume of soil pressure diagram, and apply Varignon's theorem. So if E is 0, so let's check this. If E is 0, we can use this because the application of this formula is as long as Ry lies within the extremities of the middle thirds, including Ry passing through the extremities of the middle thirds, you can still use that, and that happens when E is 0. So you just set this to 0. So Ry over B, quantity 1 plus minus 0. So that means the intensity of soil pressure at the toe and the heel would be equal, and it is uniform as shown. So that's Ry at the centroid, or at the center. QH equals QT equals Ry over B. So it is just Ry over B, but the unit here is in kilopascals or pounds per square foot, because we remember that B times 1 is in square meter supposedly, but the other partner is 1. That's why it just appears here B. So you might suspect that the unit is kilonewton per meter. It is kilonewton per meter square because the other value here is 1 meter. Then when E is B over 6, so that means Ry crosses this extremity of the middle thirds. Earlier, E is 0 means Ry crosses the center. So that's why barred X is B over 2 for that case. In this case, E is B over 6 or barred X is B over 3. Then this becomes 6 over B times B over 6. So this becomes 1. So we have 1 plus minus 1. So if we use plus, if Ry is closer to the toe, then it is 2Ry over B. Qt is 2Ry over B. If we use minus, that's the soil pressure at the heel, which is 0 because this is 1 minus 1. So this would be the soil intensity of soil pressure diagram. Ry exactly crosses the extremity or the middle thirds closer to the toe. So QH would be 0 and QT would be 2Ry over B from this formula here. And that's also the result if you equate Ry to be the volume of this soil pressure diagram, which is triangular. Then when absolute value of E is less than B over 6, so uh, that means the if this is less than B over 6, that means that Ry is within the extremities of the middle third. So this is the intensity of the soil pressure diagram. And you can always use that. So that's the location of Ry. So Q is Ry over B, quantity 1 plus minus 6E over B. Use plus for the greater soil intensity, soil pressure intensity. Use minus for this smaller soil intensity if that's the really the soil pressure diagram and Ry is really closer to the toe, and BART X for that case is uh, less between B over 3 and B over 2. That's the value of BART X. So this is the worst case and you cannot use this formula here. Instead use the fact that Ry is volume of soil pressure diagram. But however, this case is not tolerated in the actual situation, but for the sake of computations and for problem purposes, this might be the case. So, wherein Ry is closer to the toe and BART X is less than B over 3, as in this case. So that there's a portion on the base of the dam which is not in contact with the soil. So the soil pressure will be zero and only little area will be in contact with the soil. That's why QT would be increased and there's a possibility that QT will be greater than the allowable bearing capacity of the foundation. So that's why this is not tolerated. It is called the worst case. So that's Ry. This is BART X. Because BART X is less than B over 3, the entire length of contact of this soil pressure with the base of the dam is 3 times BART X as shown because that's the triangle and the center of the triangle is denoted as BART X from this QT here. So Ry is volume, so 1 half of 3 BART X times QT times 1 perpendicular to the board, where 1 half of 3 BART X is the base in this case, which is less than B, and QT is this height of the triangular soil pressure diagram, and 1 is the width perpendicular to the board. So QH is 0, QT is equal to 2Ry over 3 BART X in kilopascals also. So that's it for the discussion. This is for those who are currently reviewing for their licensure exams in civil engineering and for other engineering courses which have this evaluation on the stability of dams.